So let me reiterate this idea of conserved quantities and again say it's the most important, really the most important part of science is this idea of conservation. We couldn't do science without the idea of conservation. But the idea of if you're doing biology and a plant dies, it doesn't just disappear, right? It's what turns into the earth that then gives you nutrients for the other plants, right? This concept of conservation. In physics, the primary conserved quantities that we're going to focus on are energy, momentum, and mass. Now, we will see if you move on to 200 level physics that there is a very close connection between these three quantities, that we really can't have one without the other. So maybe it's just really one conservation idea. But for introductory physics, it's really three separate conservation ideas. So we're going to start in this chapter and talk about the conservation of energy. Then in the next chapter, we'll talk about the conservation of momentum. We have all along assumed the conservation of mass. And again, let me just reiterate the concept of the conservation of mass. You can do it with anything. Let's say I have a cup of water. That cup of water has a certain mass. If I get thirsty and I drink some of that water, and now the mass, we've changed the mass, I'll call it m prime for the mass after, m before, m prime after, then we know that the mass of the water has changed by delta m equals m by minus m prime. And where, m minus m prime, where, or you could say, you might, if you're paying attention, you could say, isn't it m final minus m initial? This would be a negative quantity because we are reducing, right? This is a negative quantity because we're reducing the amount of mass. This is the positive quantity that must have gone elsewhere, right? So it must have gone elsewhere. So where is that delta m? Did it disappear? And you say, no, I absolutely understand that you drank it. It's in your tummy, right? Mass is a conserved quantity. It doesn't go away. It doesn't just disappear. It's got to be somewhere else, right? We assumed that. We assumed we understood the conservation of mass. Sorry, I lost my train of thought. We assumed conservation of mass all the way through. We assumed that you understand that if you cut a mass in half, it doesn't just disappear. The mass has to go somewhere. Okay. So the two quantities that we're going to focus on for the rest of this class, for the next couple of weeks, is energy conservation and momentum conservation. So we're going to start with energy conservation. To start with energy conservation, we got to figure out what energy is. Before we talk about what energy is, we need to talk about the concept of work. Okay, I would like to define the concept and quantity work in physics. It is a physics quantity. And it really is the same work that we think of in real life, except we've got to be really careful about the difference between work and energy. So I will explain that. Or actually, one of the things that we've got to be really cognizant of is what is doing work on what. That's really going to become important. It's going to become an exam question where I say I'm doing work on something, or is it doing work on me, or both? Okay. Anyway. So let's just say, for example, I'm pushing with a constant force on a couch. So I'm not showing the force here. Let's go ahead and add the force in. So you can just call that F push or just F. And let's say I'm pushing at a constant force and the couch is moving at a constant velocity. You should know enough about Newton's second law now to know that that is not the only force on the couch. There are other forces on the couch. If it's moving at constant velocity, there must be a frictional force or something pushing back. There must be a gravitational force pulling it down. There must be a normal force up because it's on the ground, etc. And maybe those are all the forces on the couch. It actually doesn't matter that it's moving at constant velocity, but I did say it was moving at constant velocity. All I care about is that I'm pushing with a constant force on a couch with that force F. And let's say I want to move the couch across the room and I move it a distance d. Okay, so how much work did I do? Well, the definition of work, or I won't give you a definition of work, I'll give you an example of the work. The work done is actually just F times d. That is the work done. So if I'm pushing with a force of, let's just give me some numbers. Let's say I'm pushing with a force of 150 newtons. I don't think that's a very big force. And I move at a distance of 3 meters. Then therefore the work done is 150 newtons times 3 meters, which is 450. And what are the units? It's newtons times meters. And the newton times the meter is a joule. So let me just do some units. The joule is the MKS unit of work or energy. Now, as an aside, at a later time, some long time later, we're going to see a Newton meter as far as torque. And torque is not work or energy, but it's got the same unit. And we tend not to call torque joules, even though a Newton meter is a joule. We don't measure torques in joules, we measure torques in Newton meters. It's a little weird. But anyway, for now, the MKS unit of energy or work is a form of, work, we will see in a second, gives a body energy, is joules. Be careful, work equals FD is not a definition for work. I'm just giving you, saying that that is the work done in this case, is FD. Work is always some force times some distance, but it's not just any force times any distance, and so we got to be really careful about the definition. In this case, it is force times, it's the magnitude of the force times the magnitude of the distance because they are in the same direction. So that brings me to, does the gravitational force do work on this body? What does work on this body? I should have asked. And the answer is me. I'm the person pushing the couch. I'm doing work on the body. Now, it is true that gravity can do work. And the normal force can do work. And friction can do work. And might be in this case. But who's doing work in this case? I'm doing work because I am moving the couch. The force F is pushing the couch the distance D. The gravitational force is not doing work because the gravitational force is not moving the couch the distance D. The normal force is not doing work because the normal force is not pushing the couch the distance D. The frictional force, we will see later, does do work. It's doing negative work because it's trying to keep me from pushing the couch distance D. We'll talk about that later. But in this case, the work that I've done, the work that the force F has done, is 450 joules. So that is not the total work done. That's just the work done by me. We can also talk about the work done by gravity. Right, so that's the work done by the force. The work done by the normal force, the work done by the frictional force. I won't do that right now, but we can talk about the work done by all the forces, or we can talk about the total work done. And that's where we're going with this, is the connection between sort of the work done by individual forces and the total work done on a body. To start with, I just want to do a couple examples before we move to the actual good definition of work, solid definition of work. Now let's come back to the pulley problem. Remember the pulley problem? Where I pulled with a force Ft, but if I had a single pulley like this, then the force that I had to pull was Fg, and the distance I had to pull was h. So what's the work done? The work done in this case is I'm pulling with a force F, that was my pulling force, which is equal to Fg, and the distance I pulled was h. So the work done is Fgh, whereas the force I'm pulling with is F pull is equal to Fg. Or I can go back here and I can say, oh, in this case, the force that I'm pulling with is Fg over 2, and the distance that I'm pulling is 2h. I'm pulling 2h of rope, so I'm pulling that rope 2h. So the work done in this case is the force that I'm pulling with, Fg over 2, times the distance I'm pulling, 2h. What is it? The work done is still Fg times h. Look, it's the same. Fg times h is Fg times h. Even though the force I'm pulling with is something different than Fg. It's smaller. It's Fg over 2. The work I'm doing is still the weight. The Fg is F sub g, right? Be careful. That's not F times g. Sorry. That's F sub g, the gravitational force. So the force I'm pulling with is the gravitational force times, the work I'm pulling, careful. The force I'm pulling with is the weight over 2. The work I'm doing is the weight times h. In this case, the force I'm pulling with is the weight. The work I'm doing is still weight times h. So what is conserved? And then same thing here, right? The work done is going to be the force that I'm pulling with, F sub g over 4, the weight, times the distance that I pull it, 4h. So the total work done is still the weight of the body the weight of the body times h. So the work is the same in all three cases. So you can see that force is not a conserved quantity, work is. In order to lift the piano with this pulley system, or this pulley system, I have to do the same amount of work to move the piano up a height h. Remember, that's what I'm doing in the end, is I'm moving the piano up a height h. I have to do the same amount of work. Work is the conserved quantity. Okay, let's come back to the definition of work. Let me be a little bit more careful about this definition of work. Remember, this is not a definition. This is what it turns out to be. The definition of work in words is the work done by a force is the magnitude of the force times the distance times the distance that force moves the body. In other words, well, it's the distance that the force moves the body. So therefore, in this case, my pushing force F moves the body a distance d, and that's the force that's moving the body, so the work is done as F times d. Whereas F sub g, the gravitational force, doesn't move the body, right? It's not in the direction of d, so the work done by the gravitational force is the gravitational force times the distance that the gravitational force moves the body, which is 0. And the work done by the normal force, same thing. The work done by the frictional, well, you say, but it's not moving the body, you're moving the body. But the frictional force is trying to move the body in the opposite direction. And it turns out, we'll see why in a second, there's going to be a negative sign because the frictional force tries to slow down the body and I'm trying to speed up the body. We'll talk about that in a bit. But let me ask a different question first. Keeping in mind that the actual wordy definition of work is the magnitude of the force times the distance that force moves the body. That is actually an accurate wordy definition. When we write it as a formula, it'll make more sense. But let me first ask you a question. Let me take a different situation. Let's take the couch and carry it instead. All right, maybe it's not a couch. Let's take a box of mass m. And let me carry that box of mass m at constant velocity. Remember, over here we said constant velocity. I said that, but it doesn't matter whether it's constant velocity because the force times the distance is the same whether it's constant velocity or not. In this case, the constant velocity actually tells us that the magnitude of the frictional force must be equal to the magnitude of the pushing force. That's what the constant velocity tells us. Okay, in this case, let me take a box, lift it up, and carry it at constant velocity. What is the work done that I do on the box? Anybody know the answer? The work, let's give this person a name. Let's call them Peppy. Maybe it's not me. So what is the work done by Peppy on the box? Anybody? While carrying it at constant velocity. The work done is 0. Say, but how could that be? Peppy must be expending energy to move the box. Peppy must be expending energy even though it's moving at constant velocity. Hey, how do I know Peppy's expending energy? Because Peppy's working up a sweat. In order for Peppy to keep on moving the box, Peppy's got to eat some food, right? Eat a couple of donuts in order to get the energy to keep running with that box, right? So Peppy is expending energy, but Peppy is doing no work on the box while Peppy moves it at constant velocity. Why not? Well, let's look at a free body diagram of the box while Peppy is moving at constant velocity. Here's a free body diagram. What are the forces on the diagram? The forces are Peppy is holding the box up, so there must be, we'll just call that a lifting force. It is really just a normal force. We'll call that a lifting force. The forces are gravitational forces down. That's not a force exerted by Peppy, but that's a force on the box. So actually, are there any other forces? You might say, well, doesn't Peppy have to be pushing it in the direction of velocity? No. It's moving at constant velocity, right? So at some point, Peppy had to accelerate it to v, but it's moving at constant velocity. So there are no forces in the horizontal direction. You got to convince yourself of that. There are no forces in the horizontal direction. There was a force in the horizontal direction while Peppy got it up to speed. But now that Peppy's carrying it at constant velocity, Peppy is exerting no force in the forward direction, only in the upward direction to keep the thing off the ground. And Peppy is moving the box in this direction, displacing it in this direction. Peppy's force is in this direction, right? That's Peppy's only force. Fg is not exerted by Peppy. So the lifting force is not moving the box in the direction d. The work done is 0. And you say, how could that be, right? Pepe had to do work in order to accelerate it to velocity v, but then Pepe stops doing work on the box. But you say Pepe is and I'm repeating myself, but Pepe is expending energy. What is Pepe expending energy on? And the answer is that I guess it's a he. He is not doing work on the box. When we say Pepe's expending energy, think about the biology of what's going on. Inside your body, muscles are contracting. The heart muscle is doing work to move blood through your body, right? The muscles in your arms are doing work to move the tendons, ligaments in your arms in order to keep the box up. So work is being done within Pepe's body. So Pepe is indeed expending energy, but doing no work on the box because the force is not in the direction of the displacement. In the exact same way as the work done by the gravitational force, in this case, does no work because it's not in the direction of the displacement. So we've said that the definition of work is the magnitude of the force times the displacement in the direction of the force. That's what we said. And so now we've got to write down an equation which allows us to calculate that so it's more obvious.